Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long. In total, Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
I was very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about XLR and I enrolled in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He not only focusing on theory part, he's doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they're also conducting different exam to test our knowledge, and as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, Excella.
Recently I was searching for digital marketing courses online in Google, and I came across XLR and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped. So I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my company to join. Thank you, XLR.
Good evening, all. I hope you are doing well.
Yeah, hi. Good evening, Sushmita.
Yeah, good evening, sir.
Good evening
You
to
can,
all.
yeah, you can start the session, sir.
Yeah, sure. Hello, everyone. A very good evening to all of you. I hope you are having a great day. So today it will be our last session on EV. So tomorrow it will be started from AV. So in the EV, actually, we left with the traction inverters, DC-DC converters, that much topics, and also some controlling algorithms, that how actually we can control basically the motor drives, we can say, that is permanent magnet synchronous motor drives, BLDC drives, or induction motor drives, means how we can control the speed and the torque. So our main motive is to control the speed and the torque, right? So both are basically a dependent one. But here, one thing actually we have to keep in mind that means there is a two types of torque actually are there. One is a load torque and one is a electrical torque or electromagnetic torque, we can say. So we will see that how actually all of these things actually are controlled. So before that, actually, I will be starting with the DC-DC converters and the inverters. So as a practical example, guys, I have developed actually a DC-DC converters. Means I am just giving you the overview, obviously, and how actually you can design a step-by-step a DC-DC converters depending on your application, because I am not taking or not giving you a particular EV model DC-DC converters, but yes, means depending on your applications, actually you can easily design a DC to DC converter and inverter as well. So there is a two types of converters, inverters actually we can design. One is a hardware based model. Everything will be on hardware. Another one is a software based model, means every switching pulses actually can be controlled by your microcontroller end, right? Depending on everything. Suppose like we have seen the charger designs. So in the charger designs part, everything is controlled by a microcontroller, because as per AIS 156, we need communications, we need means soft start. So this obviously in hardware based circuit, actually we are having soft start functions, other functions, but yes, due to communication based charger it would be, so we have to use the microcontroller based models. So obviously the same type of electronics actually we are using in uh, basically in chargers. Also actually we have used AC to DC and DC to DC converters. But yes, I actually want to share with you some we can say data points, right? practical data points. Already I have shown you the design notes. From the design notes, actually you can get always the practical data points, practical datas, how actually it is performing. And performance also, various type of graphs you can see during various load conditions, various input variation conditions. So that is the main thing. Now the main thing is there is a auxiliary battery we are using. So there should be a step down converters we have to use. Or maybe suppose we are using a charger. Okay, not using a charger. Suppose we need to convert a DC, means a low voltage DC to a high voltage DC. So the only difference between the step up and step down is the turns ratio, right? Now actually I will be sharing with you a DC-DC boost converter design, means how actually you can design a DC-DC boost converters. See, uh, this topology selection is your choice depending on your application, depending on your performance, right? So there is obviously performance, cost, quality, everything matter. Now I actually used a hardware based model. These things actually we basically developed on hardware based model. Hardware based model actually, uh, I will not say that it is very easy to design, but yes, if you use microcontrollers, obviously you should have that much knowledge to means control the pulses, everything. So this type of converters actually I have started with my initial stages whenever actually I have started with my career. So on that time, actually, I have designed this, and also I have documented everything. Means how actually means how actually we are selecting the course, how actually we are selecting the number of turns, means everything. Depending on the frequency, means how to choose the frequency. So moreover, actually, I just want to explain you that how actually this type of DC-DC converter works, and we are using a transformer. So yesterday I also told that you may have some question that transformer is always working on AC. Then how actually we can use a transformer in DC circuits? So I think you may have some question. Basically, actually, we are not using a pure DC. Whatever the battery voltage actually we are getting from the battery pack, after this, actually, we are doing switching application by using any kind of integrated IC. It may be hardware based, it may be software based, right? Now, here actually I use a push-pull topology. There are multiple topologies are there, but the main motive is you have to generate a square wave signal. So obviously your switching pulse means depending on your switching pulse, actually you will get the square wave signals, and obviously depending on the switching frequency, the transformer will operate actually on that switching frequency only. So here basically Q1, Q2 is nothing but two MOSFETs actually I am using. And also you have seen that there is a center tap transformer actually we are using. Now what happens whenever there's a Q1 on, you can see that when there's a Q1 on, I1 is flowing through this direction and through the Q1. And this Q1 gate pulse is given from a integrated IC. It may be hardware based. I used actually TL494. So that is a pulse with modulation IC. Means obviously you have to select some hardware conditions, supposed to be resistor, capacitors. Also means the battery supply you will be given. You have to use some gate driver techniques. So after using these things, actually you can control this Q1, Q2, right? Now what happens, already you can actually see that. So here I1 is generating, right, the current flowing through this direction. So as a result, on the secondary side, you can see depending on these dots, right? So that is we can say dot concept. So on the secondary side, this diode will activate and we will get the output. And you can see that this diode is used for a rectification purposes. Means there is a DC and we are doing some switching application and we are generating a square wave signal. So obviously we know if there is a change in voltage, obviously So obviously we can use the transformers because it means all over the work actually depends on the induction process. Yes, there should be a leakage during this type of operations. Actually, we can get nearly 90 to 95% efficiency depending on your transformer core selection as well. The diode one, you can see it will be operating when the P2, we can say P2 winding will be activated. So during P2 winding activated, this diode D1 will conduct. During P1 activated, diode D2 will conduct. So as a result, actually we can just generating a square wave of suppose take a battery voltage of 400 volt, right? So 400 volt, by using 400 volt, actually we are suppose generating plus minus 200 volt, and means depending on the turns ratio, we have to use a step down converter. So the primary turns will be more and the secondary turns will be less. So depending on this turns ratio, it will actually step down the square waveform. But as you know that our output should be pure DC. So that is why we are using diodes for rectification. So here also you can see that the double conversion technique actually happens, right? So first we are generating a square wave, then again we are using a diode for rectification. So that is the main work. That is how actually all the DC-DC converters works. Every DC-DC converters works in such a way. Now there is a multiple topologies are there. Flyback, push-pull, forward converters. There should be cup converters and multiple ones, LLC. Now depending on your efficiency requirement, you have to choose your topology. So without any delay, actually, I just want you to share my design specs. The V input actually I have taken from a LFP battery. So the V in minimum was nearly around 36 volt. V in maximum that would be around 56 volt. So the voltage is quite you can see, right? That is and the nominal range actually I have taken 48 volt. I have used actually 15S battery 15 series. So just multiply with 3.2, you can get nearly around 48 volt. So and you can see that my target efficiency was nearly around 90%, and means my output voltage was 350 volt, and I have taken a switching frequency of nearly around 25 kilohertz. Nowadays, actually, we are basically doing a high frequency operations, not 25 kilohertz. We are using 80 kilohertz, 90 kilohertz, 100 kilohertz operations. So whenever actually we are supposed to design a high frequency operations, on that case, actually the transformer size reduced. So that is how actually in a very high kilowatt design, we can reduce the size of the overall converter, and as a result obviously we can reduce the weight of the converter, right? So means your design should be optimized whenever actually you are integrating these things in your EV. So there are multiple theoretical notes actually I have taken into considerations, and I have shared all these things. Don't worry, I will share this note for you also. Then means depending on your applications, actually you can take this process, take these steps, and easily you can actually design a transformer. What I have told you on the charger design section, that the magnetics design are the very important part of a converter. It may be inverter, it may be DC to DC, maybe AC to DC. Any kind of converters actually require a very good magnetics design. So for magnetics design, there is a lot of formulas actually I have used. I am not derivating or elaborating any formulas, but yes, by actually following these formulas, you can easily design the magnets, means primary current calculation, core selection. So depending on the BH curve, that is flux density versus frequency, actually you can select your number of turns, and you can see there are I have just given a screenshot of a core selection mechanism. Means see, suppose there is one core, suppose we can select this core. You can see that depending on the frequency, a same core is actually giving more output. So suppose this core, this first one, 814E250. So this core at 20 kilohertz, it is giving only 3 watt output power. But at 300 kilowatt, the same core can give 46.4 kilohertz. 46.4 watt. So that is how actually means power is dependent on the frequency. Means I'm talking about core power. So all is depend on the flux density. So there are multiple formulas are there. Sorry. Once. So there are multiple formulas for primary, secondary turns, means depending on your current calculation, depending on your switching frequency, actually, we have to select that inductance also, means how much inductance it should be, right? So that would be the minimum inductance, because obviously we have to store the energy, and after that it will be transferred to the secondary side. So that is the minimum inductance requirement. And depending on the frequency, there is a depending on the skin depth calculation, you have to choose the basically wire gauge, right? For any frequencies, you can't select any type of wire, right? For specific skin depth, for a specific frequency, actually, you have to choose the wire gauge. So on the right hand side, actually, you can see that depending on the frequency, you have to choose this type of wire gauge. And depending on your overall current, you have to select the number of parallel conductors. So we know obviously when the current rating will be increases, we have to use more number of parallel conductors. So that is how I have taken, see, the number of primary conductors I am using 6, and what will be the resistance of that overall means transformer, right? Because your resistance, what obviously we are using a wire, the copper wire. So this copper wire is actually having an impedance. So depending, whenever actually we are operating on DC side, so there we have to consider the DCR value, that is the DC resistance value. And depending on the current rating, actually there will be a loss, and this will actually form as a heat loss. So obviously whenever we are designing this type of converters, we have to consider the thermal point of view as well. Means we have to select that type of core or that type of, suppose, cooling systems we have to provide if the core temperature or the magnet or transformer temperature is exceed the 100 degree. Mostly we have taken maximum up to 100 degree temperature rise, but above this actually we have to use means, or we have to redesign the transformer, or maybe we have to use some thermal management system inside the circuit, right? So that is how actually we are actually calculating all the things. Means we can actually calculate the losses as well. So here I have given all of this type of means all the calculation stuffs actually I have written here. You can see the copper losses, the core losses, the total losses, right? Everything. What would be the thermal resistance? So what would be the temperature rise? Means everything can be calculated. Means you can predict how much temper, means on this wattage. Suppose you are designing a converter for 1 kilowatt. On this 1 kilowatt with this sufficient amount of current, how much temperature can rise in the magnetics, or we can say in the transformer. Now there is inductor selections also I have taken. Depending on the permeability, actually you have to choose the inductor materials as well. So there are I have given basically online design tools that from how actually you can design the inductors also. So I have given us screenshots. So that type of core selections, micrometals actually I have chosen. So there are mainly you can follow this design for magnetics calculations, right? Suppose you are doing any kind of project in your, I'm talking about any type of third year, fourth year, means any type of projects you are doing, you can follow this type of magnetics design. And you can use the hardware based ICs. There is SG3525 also you can use, TL494 also you can use. So this type of hardware based IC means I am talking about on a 10 years back. With the help of this type of ICs, actually, we have generated a square wave inverters also. Whatever the square wave inverters actually we are using on that era, means I'm talking about home inverter systems, hardware based home inverter systems. So on that case, actually, you can easily design by TL494, or obviously there should be a overall circuit, but depending on that, actually, you can easily design your DC to DC converters or maybe inverters. So I am showing you some inverter reference designs also. So I have mainly it is for UPS design, but yes, our main motive is to design the inverters. So in the UPS sections, actually, you can get all the things, means charging techniques. Obviously, there is a battery. So there you can get the charging algorithms, charging techniques, and also during obviously during cutoff or mains off condition, you can actually observe the inverter techniques. So from this, actually, you can get the overall concept, right? How actually the inverter works, how actually we are generating the PWMs, how actually we are using the sinusoidal pulse width modulation techniques. So sinusoidal pulse width modulation techniques are widely popular in traction inverter system. Whenever actually we are designing our inverters, we mostly use SPWM technique. Now, obviously, whenever we are designing a controller, for that, obviously, you should know about the basic concept of the inverter, that how actually we can generate a sinusoidal wave from a DC. After that, there is a speed control technique. So that is different thing, right? So that is a closed loop control. Depending on your inputs, right? Depending on your each inputs, actually, we are changing all of these things. So here, basically, you can get it that how actually this transform. You can see there is also a transformer. So depending on the battery voltage, suppose you are using a very low voltage battery, suppose 100 volt, 200 volt battery, and your motor voltage rating is supposed to be 400. Three phase, we need 300, 400 volt. On that case, we have to step up the voltage, right? At a certain level. From the battery voltage, you have to step up the voltage at a certain level. So for this, actually, we are using this type of transformers. But yes, all the things will be on the high frequency. So this is basically a low frequency, means I am just taking an random example. This is basically a low frequency transformer, means this 850 watt transformer is this much huge, nearly 10 kg weight. And nowadays a 10 kilowatt traction inverter weighs nearly 20 kg, 30 kg. Right? So we have to keep in mind that high frequency solutions are only solutions in the EV, not the low frequency solution. Everything, every converters, inverters, we are actually designing on high frequency basis. And especially we are incorporating with SICs, means SIC based MOSFETs and GaN based MOSFETs to reduce the loss as well as the means design size. So here they have given the schematic, means overall hardwares what they have used. So everything they have given. They given that how actually we can control the inverter. So that is basically inverter topology. There is a V battery, right? Suppose that the V battery is 100 volt and you need a AC output of nearly around 400 volt. So that is a basic operations, that how actually we are controlling these four switches. Mostly this is a single phase inverter. On we have to use for EV, actually we are using three phase inverters. So in single phase inverters, we have to use four MOSFETs or four IGBTs, right? And we have to control the diagonal switches at a time so that we can generate a positive and negative waveforms. So basically, to obviously, if you are controlling via hardware based model, they will give you only a square wave waveform, square wave. But if you require a pure sinusoidal wave, on that case, you have to incorporate with microcontrollers, and you have to use a advanced PWM technique, as advanced pulse width modulation technique. So here also they have given some sine PWM technique modeling. In TI, actually, in Texas Inverters design notes, actually, you can get a more detailed one. So they have given all the things that how we are applying the pulses in this type of diagonal switches, or means S1, S2, S3, S4, how we can turn on, turn off everything. So if you need more in detail, because obviously I am taking a overview on this. If you suppose to want design a inverter system, right? So obviously you can follow my channel on YouTube. You can easily get the MATLAB simulations on that. suppose you are specified on the PWMs. So on that case, you can check it out. But yes, for a overview, actually, we should know about that how actually the inverter works. So from this, you can get a rough idea on DC-DC converters and the inverter solute means operations, how actually it is operating. Now, actually, I want to start with the 1 second. Drive system. Okay, so I hope you can see my screen. So what are the motor control techniques actually we are using? What is our main motive? To control the speed and the torque, right? How we can differentiate these things, speed and torque? Suppose we are suppose in an uphill, right? Uphill condition. So on that case, the speed is very low. Obviously, on the uphill condition, our speed is reduced because there is a high load torque actually we are applying. So on that case, we need a very good initial torque, right? Suppose we are starting our vehicle and we want to basically climbing a hill. So on that case, actually, you need a very good initial torque. And suppose you are in a highway, on a normal road highway, and suppose your speed is nearly around 60 kilometer per hour. Already you reached 60 kilometer per hour. So to maintain those speed, obviously the torque requirement will be less. Not that much torque means you will need uh, as compared to the obviously climbing on an uphill. So what are the techniques actually we are using to basically get this speed torque, a better speed torque characteristics? So the first technique that is widely used, mainly basically FOC, means field oriented control or a vector control technique, actually widely used in the industry. Every manufacturer actually use this FOC or vector control technique because this is very much advanced control technique, and means we are getting an excellent performance on this type of techniques, and it is very common in every EV. In case of two-wheeler, in case of three-wheelers, some of the two-wheelers actually are using 6-step commutation control. The fourth one, that is 6-step commutation control, which is specially we are applying on BLDC. So in two-wheelers means low performance two-wheelers, actually we are using this BLDC because BLDC means very easy to actually we can design, but the performance is medium, and low-end EVs actually we are using. Complexity also low, but the performance is also medium. Now we are not using that much induction motors, whatever the examples you can take from the market. So we nowadays at present scenario, actually we are not using any kind of AC induction motors because there is a technique that named V by F scalar control. So this type of V by F control actually obviously that is very easy to design, but the performance actually we are not getting that up to that level. So FOC we can apply in case of induction motor as well. Means FOC mainly actually we developed FOC for permanent magnet synchronous motor BLDC. In AC induction motors also we can apply, but yes, actually the better efficiency, the better performance we are getting from the PMSM only. So that is why all are using this topology. Now there is a sensor-less control also we are using. But yes, it is not very popular in the EV domain, means sensorless control. So sensorless means I am just giving you an overview that whenever we are actually designing a FOC technique or a 6-step commutation control, we actually need the rotor position, or we can say the rotor angle. When the rotor is rotating, rotor is a magnet. For PMSM BLDC, the rotor is nothing but a magnet. So that is a North Pole, South Pole arrangement, right? So whenever it is rotating, we need those rotational angle. So for this actually we used a Hall effect sensor. So Hall effect sensor basically integrated with the stator winding, it is fixed. Whenever the rotor is rotating, so depending on that MMF, that is magnetomotive force, actually it is generating, so it is sensing those force. So sensing those force, actually it is calculating the angle, right? So obviously it need a more amount of space. It needs obviously extra cost. But yes, for low end application, or we can say for low wattage, see, for BLDC fan application, BLDC fan applications, actually we are using sensorless control, because obviously we means can't use that costly Hall effect sensors. So that is why for a cost effective solutions, we can use sensorless control. But yes, obviously in this kind of sensorless control, obviously we can actually have to take some hit and trial conditions, right, for initial position detection. Whenever actually we are doing initial position detection, on that case actually there is some jerk issue actually we observed. There is a multiple types of jerk issue, and suppose we are using same thing on a EV. You are starting your vehicle and you are just accelerating, and you are just suppose in the performance, actually you just observe the jerk, right? So obviously there should be a smooth speed acceleration, right? We means all required a smooth acceleration during acceleration as well as during deceleration. So during accelerations, actually in sensorless control, so sometimes actually we may observe the jerk issues. So that is why in EVs actually we are not using, for low end EVs we are using sensorless, but yes, for high end three-wheeler, four-wheelers, actually we are using Hall sensor based solutions and FOC techniques especially. So these are the types of techniques actually we are using. Mostly we will see the 6-step commutation control and the field oriented control. Now we will be starting with 6-step commutation control for BLDC. For doing this 6-step commutation control, first we have to know that means we have to model the BLDC motors. Suppose you want to do a simulation, right, on the MATLAB. So on that case, you can easily get this type of full module, means motor module, from the MATLAB itself, or you can actually design your own BLDC motors from the mathematical calculations, right? From the mathematical modeling, actually you can easily get it. Now actually we will be one second. I hope okay. So that is the 6-step commutation control. See, mostly in the EV, basically we are using BLDC, means three-phase BLDC motor. Obviously, BLDC is nothing but a three-phase motors. Generally, we from the name actually itself, actually we are supposed to we thought that means BLDC, that is a DC motor, but no, it is not a DC motor. It is absolutely AC motors. But yes, it is controlled by a trapezoidal waveform, not a purely sinusoidal waveform. So due to its structure, whatever the structure we are using, means basically we are using concentrated winding on the stator side. Whenever actually we are designing a motor, on that case actually we are using a concentrated winding. So depending on the stator structure, actually we are getting a trapezoidal back EMF. So I have actually shared on, I think on the second or third session, actually I have shared one video that how actually the back EMF is generated due to permanent magnet. So our rotor is permanent magnet. So whenever actually there is a rotation is happens, it actually generate a opposite force to the stator windings. That is named as back EMF. So whenever actually we are supposed to design these type of BLDC motors, so we are actually getting a trapezoidal back EMF. But in case of permanent magnet synchronous motor, actually we are getting a purely sinusoidal back EMF. So that depends on the stator arrangement. Now, obviously, BLDC and PMSM are absolutely same. The main difference is the winding on the stator. Now, in this technique, in this 6-step commutation technique, actually, we use Hall sensors. So basically from the Hall sensors, actually, we can get the position of the rotor. Mainly we have to calculate the rotor flux position. Means mainly rotor flux, obviously from the rotor flux, we have to calculate the position for a 360-degree rotation, right? But what are the drawbacks of this type of 6-step commutation control? So we are getting a very high torque ripples, and it is very less efficient than FOC. Torque ripples means torque is actually means it is directly actually proportional to the current. To control the torque, we have to control the current, right? So that means there is a high torque ripple means you can actually observe a noise. Whenever actually you can see e-rickshaw, I think you all have seen, right? E-rickshaw. So whenever the e-rickshaw motor is started, you can observe a noise, right? Electrical noise there is on from the motor side. Actually, we are getting. Suppose I hope in e-rickshaw there is a two, three types of e-rickshaw you have seen. You have seen, I think, e-auto also, right? Piaggio or maybe Bajaj. I think you have seen those autos also. From the auto itself, I think there the noise is very less. Or in the EV also, you have seen the noise. There is that much big motors we are using, but noise is very less. But in case of e-rickshaws, we have seen that there is a lot of noise. A simple 800 watt 1 kilowatt motors are actually generating a lot of noise because of this high torque ripple, right? Because they already use 6-step commutation control. This type of control actually we are using because this is basically a low cost solution. So obviously in the e-rickshaw market, obviously there is a low cost solutions actually we are using, but it actually impact on the performance, right? Now, basically, whenever actually we are having a high current ripples, so on that case, obviously there is a high amount of losses are there. We can say the core losses are pretty high. The copper losses also pretty high. So how actually we can control this? Basically, there is a 6 states are there. Suppose there is a 360-degree angle, right? There is a rotation of 360. The rotor have to rotate for 360-degree. So we are dividing this overall 360 with the 6 steps, that is each of 60-degree. Now you can see that there is a 3-phase Hall A, Hall B, Hall C. You can see that is a stator winding. In the stator winding, actually we put the Hall sensors, and you can see there is a rotor. Inside this, you can see there is a rotor one. So depending on your speed requirement, actually we are using 2-pole, 4-pole, 6-pole, 8-pole motors. So whenever actually we are increasing the number of poles, we are actually decreasing the speed, because already we know the formula, that is 120 F by P. That is the synchronous speed actually we are getting. So that means obviously depending on the number of poles, means it is inversely proportional. So obviously we can apply a high frequency, right? 50 hertz, 60 hertz, 70 hertz, depending on your speed requirement. And so that is the 2-pole machines actually, means on the diagram actually you can get it. That is basically a 2-pole. So 2-pole rotor actually we are using. Now in this each phase, whenever there is a Hall A, Hall B, Hall C, we have seen. So we are basically using a 3-phase inverter. That is nothing but a 3-phase inverter. So in a couple of minutes ago, actually, I have shown you a single phase inverter, right? That is a 2-leg actually we were using there. And from these 4 switches, actually, we are using a single phase operation. Now we are just adding one more leg, and you can see the connections as well. So by using this overall inverters or 6 switches, actually, we can control the overall 3 phases. Now, how actually we will turn on and turn off the switches, so that, see what actually we are doing. There is a 3-phase, right? So whenever actually we are applying, suppose we are turning on 2 phases at a time. So we are energizing that phase, or we can say that line. Suppose A and C, we are energizing A and C, right, at a time. So on that case, obviously there is a flux generation happen on the stator side, and this flux will actually rotate at a synchronous speed. right? BLDC also a synchronous motor, so that will rotate on the synchronous speed. So as a result, obviously the rotor magnetic field also try to catch this speed, and obviously rotor magnetic field also rotate on a synchronous speed. Depending on your poles, depending on your frequency of operations, we can calculate the synchronous speed. Now, obviously, whenever there is a rotor magnetic field is rotating, as a result, the rotor actually starts moving, because we are, see, there is a one video, actually I will share the link with you guys. So from that video, actually you will be cleared that from a pictorial format, actually you can get a better view that how actually we are commutating, means we are changing the phase sequences. Suppose AC, then AB, then BC. So that is how actually we are rotating the phases, and as a result, the rotor, the magnetic field also we are changing, and as a result the rotor also actually moving. So this is the states of the inverters. So A and A dash. So you can see A and A dash. A is the upper switch, or we can say upper MOSFET, or A dash either is the lower switch. As a result, B, B dash, C, C dash. So 0, 0, A dash, 0, 0. That means all the upper switches are off. Now B, you can see there is a 1, B dash equal to 0. So 1 means the switch is on, 0 means the switch is off. So you can see from this overall 6 switches, you can see the B phase, that is upper switches, is on, and the C dash, that is the lower switches. From the C phase, the lower switches will turn on. So if you see this video, this picture, from B phase, actually we are turning on this upper switch. From C phase, we are turning on this lower switch. So there will be a current flow direction from this positive, from this upper switch, right? And it is entering to the B phase first. There should be a current direction from B to A or A to B. There is a two different directions actually it will follow, right? So means depending on this current flow direction, actually it is generating the magnetic field, right? Now it is actually entering from the B phase through the stator winding of the motor, and after that C phase, obviously lower switch we are turning on. So obviously that will actually passes through the C winding and then this MOSFET or switch and up to minus. So obviously there should be a proper current flowing path will be there. So that is a one step, or we can say whenever the Hall effect sensors actually sense the fourth position, you can see we already have given 6 positions, right? 1, 2, 3, 4. Suppose, and each of 60 degree. Suppose here, suppose the rotor, right? Pole, north pole, south pole. Suppose the pole is rotating in such a way, right? Suppose the north pole is suppose here. Here means on this angle, 0 to 60 degree. So 0 to 60 degree, that means that is in sector 1. 60 to 120 degree. Suppose it is moving from 60 to 120 degree. That means it is in sector 2. Yes, we cannot calculate the exact angle, but we can predict the sector. In which sector actually it is. It is from 60 to 120 or 120 to 180 or 180 to 2, obviously 270, right? So that is how actually we are calculating each sector, right? 60 sector, right? So that is how we are actually getting the sensor data, the Hall effect sensor data, means in which sector it is, and depending on that sector sensing, we are actually turning on and off the switches, and as a result we are activating the stator coil, right? So that is how actually 3-phase arrangement we are doing, and that is how actually we are controlling the speed. Now obviously to control the speed we have to change the voltage, right? Means speed, there is a relation between speed and the voltage. Means whenever actually we need to obviously increase the speed, we have to increase the voltage. Means speed is directly proportional to the input voltage, whatever the DC voltage actually we are applying. So depending on that, actually it will be changed. So that is the main concept of the 6-step commutation control in BLDC. Okay, now I am not going into field oriented control. I will just show you a model. 1 second. So before that, actually, I want to show you a mathematical modeling of a brushless DC motor. So means basically I also used to follow this thing, these equations. Guys who are really means interested on this, especially motor control domain. So obviously you have to do a in-depth analysis on this. You have to do the mathematical modeling of the BLDC motors. Obviously you have to means whatever the voltage equations, whatever the back EMF equations, everything you have to consider. But in the MATLAB simulations, actually, you can easily get the BLDC model. But it is means if suppose you need a in-depth analysis. So on that case, it is better to use this type of mathematical modeling. So here everything actually in this paper they have given the VA, VB, VC, that is a voltage equations. The back EMF equations they have given the theta E, that is nothing but the electrical angles, and omega m's, all the things actually they have given here, that how actually we are calculating. You can see that, 1 second, that's zooming up. So you can see the commutation signals Q1, Q2, Q3, Q4, that is nothing but the inverter switches, right? Q1, Q2, Q3, Q4, Q5, Q6. So that is how actually the inverters they formed. And you can see the Hall effect sensors signals, which actually they are getting. So HA1, so HBHC, EA, EB, EC. They are using basically a PI controller to control the speed. Now actually I will be showing you the model. 1 second. So guys, actually I am using a MATLAB online model because in my software there is a problem. So I am just showing you this model. I hope you can see this model. Yes, you can see. I am just elaborating something. So this is basically the BLDC model. 1 second. So this is basically a BLDC model. So whatever the equations I have just I just told you from the paper. So means each equations actually I followed, and I mapped this model. So in between these MATLAB designs, actually there is a speed generator, there is a current generator, and in every blocks actually I used the state equations, whatever the equations you have seen. So I just following those things. So here you can see that everything actually I have taken into consideration. So VA, VB, VC, how we can calculate VA, VB, VC, EA, EB, EC, and how actually we are calculating the speed, how actually we are calculating the angle, rotor angle. So you can see here we are getting the double omega. Omega means the rotor speed, and then we are actually converting this into RPM, because most of the time on the EV actually we are getting the RPM value, 1000 RPM, 2000 RPM. Not only for EV, in any kind of IC engine also we only see the rotation per minute, the engine rotation, and in case of EV the motor rotation. So whenever actually we are calculating the datas from the Hall effect sensors, actually we are calculating the angle. So from that angle, that is in radian, we are converting this into RPM by using 30 by pi. So that is how I modeled everything. Actually, this online mode is not so much it's reliable. Now you can see I am taking the theta. So from the BLDC motor itself, actually, from the BLDC motors itself, actually I am getting the theta E. That is the electrical angle. Means inside the stators, whatever we are magnetizing this on that is a theta angle. That means 60 degree, whatever the 360 we mapped, and we are actually calculating the each sector of 60 degree, right? There is a 6 sectors forming the 360. So that is the electrical angle, right? And whatever the omega, from the omega actually we are getting the rotor angle. So there is a 2 angles are there. So from the electrical angle actually we are calculating the sectors. Means we are measuring the electrical angle from radian to degree. Actually you can see here actually we are converting the theta from radian to degree, because already all the things we mapped from in angle, right? 0 to 60, that is sector 1. You can see that from 0 to 60, that is sector 1. From 60 to 120, that is sector 2. From 120 to 180, that is sector 3. So that is how actually we are calculating the sectors or generating the sectors. So after that, from the sector actually we are generating the gate pulse. So already we have decided, right? From 0 to 60, if the rotor is placed between 0 to 60 degree, so on that case we have to energize, supposed to be A or B phase. So to energize this A or B phase, A and B phase, we have to turn on these switches, right? This MOSFET and this MOSFET. So that means we have to give a pulse from the microcontroller, right? So on this position, we have to give a gate pulse to the switches, right? Already we have taken a session on the MOSFETs, right? How we can control the MOSFETs. There is a 3-terminal drain to source and gate. So we have to push a gate pulse to turn on the MOSFET. So the same things actually from sector to gate pulse, actually we are using these things. Whatever the A dash, B dash, I have shown you. The same things actually I am applying here. You can see. Let me zoom in. A dash, B dash, C dash. So that is how actually I am giving this. I will share this model with you also. If you have installed your MATLAB version, you can analyze this model very easily, very clearly. And obviously, you can change it accordingly. Suppose you want to be for 1 kilowatt model, 2 kilowatt, 3 kilowatt model. Obviously, you can design by your own to change these all the variables. Now you can see this get pulse is given to the 3-phase inverter. So on the upper side, you can see there is a 3-phase inverter model also I have used. But here in this 3-phase inverter model, we are actually applying a gate pulse as well as a control signal. So from where actually we are getting this control signal, we have to see that one also. So you can see that, okay. That is not a load torque, 1 second. That is basically a speed reference. So that is basically a speed reference actually we are giving. Now speed reference means, see, there is a 2 types of model we can apply. One is we need an acceleration on the EV, right? Suppose it is at 1000 RPM, we need an engine RPM up to 2000 RPM. So that is the same thing actually I have given. At 0 step time means at the initial state it is 1000, right? Also, okay, sorry. At initial speed that is 0, 1000 RPM after 0.5 second. Okay, suppose to be 0. My God, this is not actually right. So initially it is in 1000 RPM, right? After 0.5 seconds, we need an acceleration. When from after 0.5 seconds, we need a 2000 RPM motor speed, right? So on that case, we are applying a reference speed from the pedal, whatever the acceleration pedal actually we are using. So from that acceleration pedal, actually we are giving this input. Now we are also sensing the actual speed of the motor. We are giving a reference speed and we are also sensing the actual speed of the motor. Now, inside this controller, what is this inside this controller? That is a basically PI controller actually we are using, means proportional integral controller, right? So there is a concept whenever actually we need to reduce the error. Suppose 1000 RPM we are giving. But in an open loop condition, see, everything is in the closed loop control. There is in over the world, whatever the controlling actually we are doing, all the things are closed loop controlled. Suppose there is a converter we are using. We need to convert 240 to 20 volt, suppose 12 volt auxiliary. So on that case also we have to sense the output voltage, that whatever the pulse width modulation we are doing, is it proper to produce 12 volt? So from that actually we are giving a feedback to the controller, and depending on that feedback actually it is actually controlling the pulses. Same here also, we are giving a reference speed and we are also sensing the actual speed. Suppose we are giving 1000 rpm and it will just sense that it is 900 rpm. So to basically eliminate this gap, right, this 100 rpm gap, it will actually reduce the error, right? Reduce the error, it have to increase the voltage, right? To increase 100 rpm, it have to increase the voltage as well as the current also. Now you can see that here basically, see, this is a PI control, that is also a different concept. Means it is basically in control systems we have seen, whenever we learn about control system, on that time we seen the P proportional controller, I for integral controller, and also D derivative controller. So PID control systems actually we have seen on the control system part. So I am not going into deeper that how the proportional constant we have to select, what are the methods of calculating the proportional constant, integral constant, derivative constant. So obviously I'm not going into that deeper, but yes, I've used PI controller only, not a PID controller. And by using this PI controller, actually I am minimizing the error between the reference speed and the actual speed we are getting, right? So that is actually our control signals we are generating. So this control signal actually we are giving to this inverter section. Now you can see that, see, this is basically an online model. So that is why this type of things actually we have seen. Basically this is a control voltage source, DC control voltage source. So we are giving this control signal to the DC to DC converters, right? Whatever the battery pack voltage we are getting from this, we are actually in the inverter operations. I have already shown you there is a transformer operations, right? So depending on that, actually we are increasing or decreasing the voltage. So this control signal actually we required to increase or decrease the voltage of that inverter input. So whatever the inverter input voltage we are giving, so that can be changed by this controller. And we are getting the gate pulse, right? Gate signals means switching operations, switching signals from the microcontroller, right? And obviously how actually we are getting all the calculations, all the sensing data we are calculating inside the microcontroller. And from that actually we are giving the gate pulse. And this is basically a universal bridge, means that was actually a three-phase inverter circuit. Because I am showing in a MATLAB online model, so that is why in this is a latest model actually it is taking. So in this latest model actually this type of blocks have not used, means they are changing this model operation. So that is why this type of red marks actually they have you can see. Now I have also applied a load torque. Okay. Okay, so you can see that here also I have applied a load torque also. So means this load torque is any kind of load torque it can be. Suppose after 0.2 seconds, suppose the road is not that much, right? Means there is a suppose, means it can be anything, any kind of load torque we may apply. Maybe the vehicle weight is increasing anyhow, maybe you are up climbing, right? So initially the load torque actually we have applied, that is zero load torque. Obviously that should not be zero, obviously, but for a simulation point of view actually I have taken as a zero load torque. And after 0.2 second, after 0.2 seconds actually we are applying a 2 Newton meter load torque, right? Now we will see that how all the things actually impact in the voltage and current demand. means how actually the speed is controlling. Now actually I am showing you, because on this model actually this can't be controlled, means because in MATLAB online that can be run, right? So I am sharing with you so from here actually you can get the overall waveforms. So after running the simulation, what happens? So this is basically that speed characteristics. So what we have given that on the initial state that is 0, means obviously not 0, we have given the 1000 rpm, right? 1000 rpm. So obviously whenever it is starting, so there is a dynamic response. You can see there is a dynamic response, but after some millisecond, that is nearly around supposed to be 50 millisecond or 40 millisecond, it actually constant to a certain level, that is a 1000 rpm. If you are not applying the closed loop control, it will not actually match the 1000 rpm. It should be lower than the 1000 rpm. But as we used the closed loop modeling, so that is why our PI controller actually minimize the error between these two speed. So that is why the after 40 millisecond, it is absolutely stabilized at 1000 rpm. Now you can see that at 0.2 second, after 0.2 second, there is a sudden speed drop. So what we have done at 0.2 second, we are applying a load torque. So as we all know, whenever we are applying an external load, right? So on that time, obviously speed will be reduced, right? Now what happens? There is a two type of torque are there. One is electromagnetic torque, one is a mechanical torque. So whatever the torque actually we are applying from externally, that is nothing but a mechanical torque. Now what happens when mechanical torque we are applying? So obviously electromagnetic torque will be on the whatever the torque values would be. Suppose initially it is 0, not actually 0. Just take it as a 0 or 1, right? So electromagnetic torque will be on the equilibrium condition, means it will also be 1. So whenever we are applying a certain load torque 1 to 2, suppose that is 1 to 2 or 0 to 2. So electromagnetic torque also means it will be increased up to 2, right? It will catch that torque, right? Now, how actually it will reach those torque, 2 Nm torque? Obviously, it will drawing more amount of current from the controller, right? Whenever actually we are applying a load torque, actually it will draw a more amount of current. Now after 0.5 second, you can see that there is a step change. What? Because we have actually changed the reference speed from 1000 rpm to 2000 rpm. Now we want to accelerate. Now how actually this is accelerating? You can see that whenever we are actually applying the acceleration, on that immediately there is a dynamic response. It is obviously there is a delay to catch those speed. But you can see after roughly around 100 millisecond, it is absolutely stabilized at 2000 rpm because of those PI controller, right? So you have to properly tune whenever actually you are into the deeper on these things, you have to properly tune those PI controllers, or maybe means everything actually you have to control via coding and everything, right? So that is the speed graph. Speed, whatever the speed actually we are giving, that is a speed graph. Now let's see. Now we will be seeing the back EMF. So this is basically the back EMF. You can see at first it is nothing but nearly around 60 volt, around 60 volt. After 0.2 second, there is a sudden drop in the voltage. I think you can observe there is a little bit dynamic response actually we observe at 0.2 second. After 0.2 second, as I told you that voltage means speed is directly proportional to the voltage. So we are actually increasing the voltage, input voltage. So as a result, the back EMF also increased. Right? The speed is increased as a result, the back EMF also generating more. So after 0.5 second, there is a increment in the back EMF, right? And you will see that how this is actually a proper trapezoidal back EMF we are getting. So whenever actually you will design a BLDC motor, so you will absolutely get the proper trapezoidal back EMF. Now actually I will be showing you the current waveform, right? Okay. Now I will be showing you the current waveform. So this is basically the current waveform. You can see that initially it is supposed to be 15 ampere or something around this 15 ampere. After 0.2 second, as we applied a external load torque, mechanical load torque. So obviously to be in the equilibrium condition, so this electromagnetic torque will be increased. And I already told you that torque is directly proportional to the current. So we have to increase the current demand. So that is why actually you can see that after 0.2 second, there is a current increment and that is stabilized. After 0.5 second, there is a again current increment as we already increased the speed. So that is why actually we need more load torque, right? More torque will be generated. So that is the current waveform, how actually it is changing depending on the mechanical load torque as well as the speed references. So if you see practically, there is a so you can see that is the basically ripple that is not properly sinusoidal due to the back EMF operations. Whatever the back EMF we are getting, that is trapezoidal. So due to this trapezoidal back EMF, actually we are getting this type of ripples in the current. So as a result, whatever the electromagnetic torque actually we are generating, there is also a ripple. So that is why whenever actually we see this type of BLDC motors, on that case actually we observe some noise, right? That is basically a electrical noise. So obviously whenever we are in FOC technique, field oriented control technique, so this type of noise actually eliminated because there is no torque ripple. In this current waveform actually you can get the peaky nature, right? But this is in the properly sinusoidal waveforms actually this type of ripples actually eliminated. So in the FOC technique actually we can get those type of proper sinusoidal waveform. So this is basically on how actually we can control the BLDC motors. Now actually I am giving you a small break. After that I will show you the PMSM means FOC technique. I will not be showing the means in depth this MATLAB model, but yes, I will show you the concept how actually we are applying the FOC, right? So just taking a 4 to 5 minutes break, and after that we will start. If you guys having any question, please you can ask regarding this control algorithms, because obviously it is an in-depth electronics thing, but yes, obviously it is a very crucial for EV that how actually we are controlling the speed and the torque. It is the main thing, right? In the IC engine, everything is on the IC engine, right? So how actually we are using the cylinders, how we are applying the petrol and air mixture, and we are using a spark plug, right, to generating the spark. And obviously using this spark actually the pistons is moving. So that is how actually we are moving the wheel, right? So yes, in the IC engine based vehicle that is totally different. In case of EVs, that is the main thing. That is how actually we are controlling the electric motor. So obviously it is very important for you also, that how actually we are controlling the overall inverter switching, overall DC-DC converters voltage, overall speed, overall mechanical arrangement, overall electromagnetic torques, waveforms, right? So each thing actually there's a dependency. So basically, guys, in field oriented control, that is a vector control we can see. Now that is a pretty complex controls actually we are applying in a PMSM, BLDC or AC induction motor. In everywhere actually we can apply these things. So 6-step commutation control, we don't need that much complex algorithms. Means just we need to turn on the switches accordingly, depending on the Hall effect sensors. But in the FOC actually we have to control the current loop, voltage loop, conversions. There's a lot of things actually we have to do. But yes, as a result, we are getting the precise torque control, and there is no torque ripple, no noise on that, and very high efficiency actually we are getting from this type of field oriented control. So we are actually applying this type of control in the PMSM, especially permanent magnet synchronous motors actually we are using. So on the permanent magnet synchronous motor, we are applying this FOC technique. You can take any example from the Indian market. Tata, means you can take Suzuki, you can take Mahindra, right? And whatever the EVs actually we have seen on the market, there is Hyundai also there, BYD also there. Everyone is using PMSing and everyone is actually applying the same field oriented control technique, right? The main purpose to use this field oriented control technique to get a better torque control. Whatever the torque ripple actually we are getting on that BLDC, means 6-step commutation, not only BLDC, that 6-step commutation. So that can be reduced. The torque ripple can be reduced. Obviously, then we can precisely control the electromagnetic torque from the stator operations. Also, there is a very smooth speed range actually we can do. Now, what is the actually control algorithm? So it is basically a quite big thing. It's from this overall block diagram. You may have seen that what is this type of control technique. But yes, I am just giving you very easily. There is a multi-level inverters you can see, means that can be anything. That nothing but a three-phase inverters actually we are using. So there is a IA, IB, IC we are taking. See, the main focus from, not from here. One second, guys. From this application note, actually, you will be getting a very good idea. So that is basically how we are actually wounded the primary winding. That is a stator coil. So 3-phase, and in each phase actually we are using 2 slots. It may be 3 slot, means it actually depends on your stator pole and rotor pole. How actually you are choosing. Depending on your speed range, actually you have to, means that is on the motor design part. For one phase, you are using 2 stator slots. 3 stator slot, 4 stator slots. So as a result, we are actually giving more number of poles or more number of slots, right? So whenever actually we are doing this type of more stator winding, we are actually can control a very precisely, right? A very low angle actually we can do by using this arrangement. Actually, you can see 180-degree phase displaced from the B phase itself. Also, it is 180-degree phase displaced, and you can see there is a permanent magnet. That is a basically 2-pole. You can see north pole, south pole, but most of the time we use 4-pole, 6-pole PMSM. 4-pole also very popular. Now what happens? We need this rotor rotation, right? We need this. We need to control this rotor flux, right? So if we can control the rotor flux, we can control the rotor speed, right? So that is how actually to control. See, we are not directly involved with the rotor. We only involved with the stator winding. From the BLDC also you have seen that we only controlling the stator magnetic field by the inverter switching operation. In FOC also we are doing the same thing, but yes, that is a sinusoidal waveform. So that is how actually means we are doing a vector control. So why it is named as vector controlled? 1 second. So basically when I will be showing you the okay, this is the rotor flux position. Yes. Now we have to actually know the rotor flux position, where the rotor flux is implemented. Now, in the vector control, the main concept is whatever the stationary phases we are using. ABC, the stator winding, that is nothing but a static, right? That is stationary. ABC. So we are actually converting this 3-phase to a 2-phase system. So these ABC systems actually are converted into a alpha beta system. So this ABC, you can see that this A phase, B phase, C phase, that is 180-degree phase displaced to each other. So that is basically converted into alpha and beta winding. So you can see that is alpha, that is beta. So that is 2 winding parameters, actually 2 phase parameters actually we are getting. But that is also a stationary phase. Now we are converting this alpha beta quantity, this 2-phase quantity, to a direct and quadrature axis quantity. So that is basically a conversion from the stationary frame to the rotational frame. So DQ is nothing but a rotational frame. So that is why we are changing the references. From ABC, we have to move to 2-phase. From 2-phase, we have to move to rotational frames. Whenever actually we can map those rotational frames, we can map the rotational flux. So means obviously depending on this D means direct axis and the quadrature axis quantity, we can actually get the current waveforms. You can see that there is a depending on this D and Q axis, actually we are mapping the VS, that is the reference voltage, or we can say reference flux. What is the rotor flux actually there? This rotor flux actually we are calculating by using this overall transformation. This rotor flux is actually moving, right? From supposed to be, you can take that is as a 0-degree. So from 0-degree actually it is moving 0, 0, 1, 2, 3, 4 means it is actually doing a 360-degree angle, right? That is how actually the overall rotor actually rotating. So obviously we know that in a permanent magnet synchronous motor, what happens? The rotor flux, in which speed the rotor flux is actually changing, the rotor also actually taking the same speed, means where the rotor flux is positioned on that immediate phase, actually the rotor pole also or the actual rotor also placed on that angle only, right? So that is how actually means PMSMs also pretty much we can control easily rather than an induction motor, because in induction motor that is asynchronous operation, means rotor flux is not equal with the rotor speed. there is a sleep, right? In induction motor, in asynchronous motor, actually there is a sleep between the rotor flux and the rotor. But in case of synchronous motors, actually there is no sleep actually. So exactly it is equal, the rotor flux and the rotor speed is exactly equal. So that is from this direct and quadrature axis frames, actually we are calculating, or we are actually generating the rotor flux, means we are getting the position. So obviously there is a Hall effect sensors also we are using, the same Hall effect sensors, right, in on the stationary phases. So we are getting from that Hall effect sensor. So you can see there are 2-3 types of conversion are there. So this ABC to alpha beta conversion is named as Clark transformation. From alpha beta to DQ conversion, that is named as Park transformation, right? So on the block diagram, actually I have given the same thing. So you can see the block diagram. From this inverter output, we are sensing the IA, IB, IC. And from this PMSMs, from this synchronous motors, actually we have applied a Hall effect sensor on the stator side. So from the stator itself, actually we are getting the rotor position. So from the rotor positions, actually we are converting this position in the BLDC. Same BLDC, actually we are getting the speed. From the rotor angle, from radian, it is converted into RPM. So we are actually giving a reference speed here, same as BLDC. From the reference speed and from the actual speed, we are getting the error. And we are using the PI controller to reduce this error. So after the PI controller on the BLDC segment, we are getting only a control signal. This control signal we are directly feeding to the inverter, or we can say before that there is a DC to DC controller, right? Voltage controller. Now, in this FOC technique, actually, we have to control the direct and the quadrature axis current to control the torque. Torque is directly proportional to the current. So that is why we have to control the inverter current, right? Depending on the switching state. Whatever the switching state we are applying, depending on the current rating, means obviously whatever the torque actually we require, depending on that, we are controlling the current. Our main reference means why actually we are getting a very high initial torque in the PMSM motor. Because in the controlling itself, we are doing this ID, that is the direct access current, as a 0. We are actually applying a 0 current on the direct axis, and we are applying the torque reference at the quadrature axis. You can see there is a T to I, that is torque to current conversion, and we are applying a IQ reference, that is the reference current actually which we are getting from the speed. So from the speed reference, we are converting this into the current reference. So in the current reference, there is a 2 current loop. That is basically a closed loop. There is overall 3 control loop actually we are applying. One is speed control, and there is a current control. So inner loop is actually a current control loop. Now we are controlling the ID reference and the IQ reference, right? So ID reference actually we are doing it as a 0. IQ reference actually we are applying from the speed reference, or we can say from the torque reference, right? After that, same PI controller we have used again. So in the overall model, we use 3 PI controller. So from this PI controller, we are getting the voltage references. That is VQ reference, VD reference. Same as we are getting on the BLDC. From the speed itself, we are directly applying those voltage reference to the inverter. Here also we are getting the voltage reference on the, means after getting the voltage reference, we are actually applying from this voltage reference, we are actually generating the gate pulse. Again, you can see that we are converting this DQ quantity into alpha beta quantity by using inverse Park transformation. So in the preliminary or the primary stages, we are applying Clark and Park. In the output stages, we are actually using, or we can say in the gate driver stages, actually we are applying inverse Park transformation, inverse Clark transformation, right? All of these things actually we are applying on the algorithm. whatever the softwares actually we are creating on that algorithm, actually we have to code these things. Now DQ quantity is converted into alpha beta. This alpha beta is again converted into ABC. So from this ABC means obviously voltage have changed, right? So there is a very we can say advanced PWM technique actually we are using, that is space vector PWM technique. So this space vector also a huge concept are there on the space vector PWM technique. So means in this space vector PWM technique actually we are generating the switching pulses for the inverters. Whatever the inverters we choose for BLDC, the same inverters we can choose here. I just written this multi-level inverter because whenever we are using multi-level inverters, actually we can get a better sinusoidal waveform, right? So from the normal three-phase inverters also we can get it very easily. So that is the main difference in between BLDC and our FOC, that is a field-oriented control, right? So I have written how actually everything is actually generated, converted. Now on the if there is a difference, means obviously in the control strategy, basically we control the stator magnetic field relative to the rotating reference frame. Now we are in the 6-step commutation control, we control the stator current with a fixed sequence. There is fix, right? In 60-degree, every 60-degree we are changing the switching operations. But in case of FOC actually, we are sensing the current, right? In BLDC means in 6-step commutation, we are absolutely not sensing any kind of current, right? We are not sensing the current. We're only sensing the means rotational angle, obviously, and the electrical angle and the speed. Only this is we are sensing, right? In case of FOC, actually, we have to implement the sensors also, current sensors. The current waveforms is absolutely sinusoidal, but in case of 6-step commutation control, it is trapezoidal. Performance, obviously, we are getting better performance, efficiency, and smooth torque operation in FOC. But in case of 6-step commutation, there is a lower dynamics, less efficient, and torque ripple will be more. As a result, obviously, more current ripple as well as the more noise. Complexity, yes, FOC is very means complex to implement. There is a more number of hardwares actually we need. In 6-step commutation, lower complexity and less hardware we needed. So application, we know that high performance motors, robotics, CNC machining actually we are using. And 6-step commutation, we are using low cost BLDC motors, tools, fans, actually we are using this type of controlling. Okay. Now actually I will share with you. So that is basically on FOC, right? So there is 3 types of controls we have seen. Speed and current control, as a result, how actually we are controlling the torques. Now I will show you how actually we are calculating the range estimations. How actually we are calculating the EV range. Means suppose we need a 500-kilometer range, how actually we can design the battery packs? What are the losses? What are the parameters actually we have to keep in mind? So there is an energy management system actually we are using in EV. First one is a battery management system, as we all know, that is absolutely controlled, means controlling the battery parameters like voltage, current, temperature, state of charge, everything. In the energy management system, basically we are controlling the battery power flow to the motor power flow. Suppose it is a HEV, then from the generator input current we are getting. So depending on that power requirement, we are actually managing those current to charge the high voltage battery pack, or maybe the same current actually, the same power actually we are giving to the motor, right, by using PSD. So this type of overall power management actually we are doing via EMS, and only battery controlling we are doing via BMS, right? So that is the main difference between BMS and EMS. And how actually we can do the energy efficiency, how we can improve the energy efficiency. So driving habits, if whatever the acceleration decelerations we are actually applying, so depending on that we are implementing those mode of operations, right? Utilizing regenerative braking, so obviously not applying the brake, right? We even whenever actually we are decelerating, what is the concept? That is, during decelerations actually we are generating the power. So obviously we have to keep in mind these driving habits, that we can more regenerate the power rather than we are using the mechanical braking. And obviously maintaining the optimal speed. In case of IC engine also there is a same point actually we are following, right? Maintaining the optimal speed. So every time actually they are giving that proper mileage on a proper speed range, right? That should not be very lower, that should not be very higher. That is the optimal speed range they are giving. Same as for EV also. And reduce obviously unnecessary loading. Whatever the mechanical load or actually we are applying externally, actually it will affect your overall range and everything. Now, fourth one is a smart charging. Whatever the V2G, G2V already I have told you. So that is also we are implementing, but we always prefer the off-peak charging. Means charging during the off-peak hours, which can actually reduce the grid strain as well as the power or the energy cost. Uh, Everything actually I have taken into account, dynamic charging, everything, and data analysis and optimizations. Whatever the driving habits actually we are analyzing, all the data actually we are actually giving to the server, right? So depending on that data, actually we can do a real-time calculation, real-time data collections, so we can get the battery health properly, we can show the driving pattern properly, right? And we will easily calculate the energy consumptions depending on that driving pattern. So that is how actually everything's actually we are managing, so via EMS solution. Now there is some real world energy consumption benchmarking actually we are using in any kind of EVs. Whenever it is in city, that is a light traffic, the consumption is nearly 100 to 130 watt hour per kilometer, right? Whenever that is in urban or stop and go type traffic, so that is 130 to 160 watt hour per kilometer. That is the energy consumption. So you can see that is in highway more than 100 kilometer per hour, the consumption will be more. So obviously depending on the, see, whenever we are using a EV and whenever there is a traffic, your EV will not consume anything. But in case of IC engine based vehicle, whenever you are in traffic, right, you are stopping and your engine is on, so it is actually consuming your fuel, right? But in case of EV, it is absolutely consuming zero. Yes, obviously you are using auxiliary loads, like suppose you are turning on the ACs, you are turning on the heater in winter cases, so obviously it will consume a little bit, but without this there is a no consumption. The motor will be at its stall state, right? Now in the aggressive on the sports modes, actually we are getting nearly 200 to 300 plus watt hour per kilometer. Now depending on the motor RPM, what is the maximum power consumption, or we can say the peak power consumption? So from 0 to 2000 RPM range, the load type we are taking as a very much low. So that is why on that time, the maximum peak power we can draw nearly around 2 to 10 kilowatt. So for a PMSM, actually I am giving this data. From 2000 to 6000, that is nearly around 10 to 40 kilowatt. And you can see that with respect to the speed also, 40 to 70 kilometer per hour. The RPM from 6000 to 12,000, the load type is high, and the power draw is from 40 kilowatt to 100 kilowatt. And in the sports mode, acceleration mode, when the RPM range is means 12,000 plus, on that case, it can draw up to 300 kilowatt peak. Porsche also using 320, nearly 300 kilowatt motor. So obviously, whenever there is a sports mode, actually we are activating. So on that rapid acceleration, so on that case, actually it can take up to 300 kilowatt of peak power. So that is the overall consumption. Now I am giving you that which type of motors and which RPM maximum power and how much average consumptions actually we are getting. That is basically a case study. Tesla Model 3, they are using PMSRM motor, new technology. The maximum RPM it is nothing but 18,000 RPM. The power consumption is nearly around a 182, sorry, not power consumption, that is a motor power rating. Max power rating it is 200 kilowatt. Efficiency is nearly around 90 to maximum 95% depending on the control algorithm. The average consumptions you can see that for nearly 140 to 160 watt hour per kilometer. So obviously you can roughly design, right? Suppose we need a 500 kilometer of range. Then how much battery pack capacity we can, means we have to design the minimum battery pack capacity. Now Nissan Leaf AC synchronous motor, 10,500 RPM, maximum 110 kilowatt, 85 to 95% of efficiency, and you can see that 150 to 180. Porsche Taycan is using dual PM SRM, 16,000 RPM each, and the power that is a cumulative power for two motors, that is 460 to 560 kilowatt. That is for two motors. Efficiency nearly around 90% we can take, and the average consumptions that is a cumulative consumption that is 210 to 250. So BMW i3 AC synchronous motor, 11,400 RPM, 90% efficiency, means this BMW i3 is nothing but a series hybrid vehicle. Okay, sorry, BMW i3 EV model actually I have taken. There is a hybrid model also there. So this is a rough idea of the energy consumption. Now I will be showing you that what are the actual factors are there. Means what are the main factors are there. We can say the losses criteria, the everything. So let me share with you. So this is basically a paper. So what are the major losses are there? The major losses, especially on the rolling resistance work. If I am talking about the some mechanical losses will be there, obviously. Depending on the weight, we are using obviously the tire. So there is a rolling resistance. Depending on the road conditions also, there would be some rolling resistance. Depending on the weather conditions also, there will be a rolling resistance. After that, there is a aerodynamics work, right? Depending on your mechanical designs, obviously there is a aerodynamics will be there. So there is also a loss, right? Now there is a potential energy change depending on the elevation. If means type of road which we are selecting, or supposed to be it will actually predict in which road actually you are. I already talked to the EMS solutions. In EMS basically we are absolutely taking the driving habits, the road conditions, every day's traffic conditions. We are actually adding all this data, and from that actually you are giving, they are giving the range. So from the overall thing actually it is dependent, right? Now there is a everything also depends on the kinetic energy change, right? And kinetic energy change also depend on the weight and the speed. Now there is a traction power also there. There is a transmission system also there. Suppose this is a HEV, there is a gear ratios, there is everything. There is a PSD. So depending on that, actually there will be a losses. If there is a pure EV system, obviously there is a transmission, there is a mechanical shaft and gear system already we are using. CVT we are using in case of this type of system. Actually, we are using CVT, means this is nothing but an automatic type of gears actually we are using on this. So obviously there would be a gear losses, right? There should be efficiency on that also. After that, whatever the motors actually you are choosing, it's supposed to be induction motor, PMSN. Actually, this model, whatever the papers actually I am showing you, they have taken a induction motor reference, means they have taken a vehicle and they actually take all of these things means all the aerodynamics, rolling resistance, road, everything they actually have calculated properly. Means I am talking about whatever the presentation you have seen, that is the average consumptions. But for particular in detail calculations, in depth calculations, actually you need to follow this kind of means obviously this kind of losses. You have to also take care on the part of the inverter efficiency calculations. On the inverter, there is a conduction losses, switching losses, right? Magnetics losses. So in traffic, so depending on the traffic scenario, you have to segment those traffic conditions. So there should be a efficiency, right? There should be a traffic losses as well. And now there is an accessory, that is auxiliary power, whatever the auxiliary battery we are using. So there is a DC-DC converters also we are using. So we have to charge those, or we have to actually operate those auxiliary systems as well. Suppose air conditioning units, wipers, lights, sound system, everything, whatever we are using in case of EV. After that, there is a SOC estimation, means state of charge estimation, as well as we have to showcase the range, whatever the range actually we are getting. So from the calculations itself, we have to show the data to the users, right? Now, what are the in-depth calculations actually we are applying? Suppose we are starting with the environmental factors. So here actually you have to take all of these things, rolling resistance, whatever, which driving route you have chosen, is there any kind of hilly region or not, what are the type of roads, how much tire pressures actually you are having on that time. So everything depends. So how actually we can calculate all of these things? So obviously you have to take some reference, obviously. So they have given all of these things, how actually potential energy change. So we have to consider the vehicle mass, and obviously there should be a acceleration due to gravity, and also it depends on the root structure. Is there any elevation or not? So that is how actually we will calculate the energy from the P gravity. You can see there is uphill condition or a downhill conditions, depending on the road, actually it will be calculated. And after that, there is a kinetic energy change. They have taken this formula for this, the traction power due to acceleration and the deceleration. So whatever we are using rapid acceleration, means this is basically a driving habit, right? So how much means for this, actually the vehicle weight also we have to consider, right? How much speed actually we are changing from, supposed to be 0 to 5 seconds, 0 to 10 second, right? So this type of things actually we have to calculate. Now there is a aerodynamic work. So in the aerodynamic, actually you have to take the air density, also the vehicle frontal area, what would be the wind speed, right? So means the direction of the wind also you have to take into consideration. So this type of things actually you have to consider whenever you are calculating in depth. You can see that the direction of the wind, the direction means direction of the EV, means the heading angles. So from this actually we can get the power aerodynamics, P aerodynamics, how much power actually it is taking, the rolling resistance. So from this actually we can get the means we have to consider the tire pressures, alongside the what are the road conditions are there. So these things actually we have to calculate. If there any kind of means probability of rain or not, obviously during rain there is a external load, that is nothing but a mechanical load actually we are applying, right? In the driving systems there is a gear ratios are there. So that is G, how actually we are calculating these things. After that, there is a modeling of induction motor. If you are using PMSM, so you have to model the PMSM losses. So in the induction motors, they have taken the copper losses, right? Copper losses, they have taken the core losses. So means whatever the electromagnetic losses actually we are having. So this is basically motor losses. Now there is a switching losses are there. We are using, so in between core losses also there is a two segment. There is a eddy current loss, there is a hysteresis loss. So how much actually losses will be there? For proper modeling in induction motor, whatever the bearings actually we are using, so whatever the friction and windage losses are there, so we have to calculate those losses as well. Now modeling the inverter losses, we are using the inverters. So there is a MOSFETs, IGBTs, means switches we are using. So they are depending on your switching frequency, there would be some switching losses. There should be some conduction losses, right? So each and every calculations, each and every point actually you have to take into consideration. So in inverter, we are using the diode also. So for diode also, you have to, whatever the anti-parallel diode actually we are using in MOSFETs, IGBTs, on that case, from freewheeling options, actually there will be a diode losses also there. So that is the formula actually how actually we can calculate the diode losses also. After that, there is a traffic conditions they have taken. So which type of traffic conditions they have taken? That is the highway without stops. Means in per kilometer, there is no stop, right? They segmented it as a one light traffic condition. That is nothing but suppose there is a one stop per kilometer, same as followed by the moderate traffic and the heavy traffic. So that is how actually they are means segmenting those traffic conditions. So after that, there is a auxiliary loads will be there, supposed to be air conditioner. So how much would be the air conditioner power? So if that is a winter, we are using suppose heater. So in that case, how much the heater power would be? So that things actually we have to take it into consideration. Windscreen wipers also, they are also having, suppose there is a rainy conditions and your wiper is actually on the on state, so on that time it will take also a power, right? So with these powers also we have to take. And also there is a lightings are also there, it is a obviously compulsory thing. Now there is a total estimated power and the current drawn from the battery. So they have taken all the powers, right? P traffic, P AC, P lighting, P Y. That is the auxiliary battery pack power actually we are calculating. Now there is a SOC estimation. So whatever the techniques we have already we modeled, right? Supposed to be Kalman filter, supposed to be there is a obviously OCB we are not applying anything. So there is whatever the current mode, that is age, right? Coulomb counting techniques actually we are using. So that type of age counting you can see, they also taken that references, that is a prior value of the ampere hour and the corrected battery capacity. So that is how actually they are calculating the SOC. Now they have given all the things, all the formulas. Now they actually given the proper validation. So they have shared here the proper validation report. How much, see, the EV parameters they have taken, the motor means the vehicle weight is nearly around 1340 kilogram. The rolling resistance coefficients at dry condition that is different, at wet condition that is different. So what is acceleration due to gravity? Obviously that is same 9.8 meter per second for every cases. The air density they have taken for the particular area on that particular weather condition. Wheel radius, that is also you have to take. Frontal area, drag coefficient and the gear ratios. So they chosen this roadmap and this is the vehicle. They have chosen roadmap and converted to, they have taken a Hyundai Getz. So that is the overall system efficiencies they have taken, how much range actually they are getting. So they mapped all the datas, all the speed datas, means acceleration, deceleration. So everything's actually they have given here. Depending on the vehicle speed also, how much time it is actually constant, right? From 0 to 1600 seconds, actually they have given all the things. Now there is a traction power. So depending on the elevation, means there is a uphill, downhill conditions also there. So depending on that uphill, downhill, how much powers actually it is taking. Whenever there is a downhill, there is a deceleration happens and there is a low power consumptions happens. So that is the data points actually they have taken. So you can see the motor is roughly around 30 kilowatt induction motor. The rated frequency, that is 60 hertz, they have taken. The number of poles, that is 4 pole. Stator resistance, rotor resistance, stator inductance, magnetizing inductance, rotor inductance. Means obviously from the resistance and inductance you will get the impedance. So depending on this impedance there will be the losses you have to calculate. That is the total motor losses during this means overall period of time. And they are also calculating the motor efficiency. Sometimes you can see that the motor efficiency that is 0%. It is not possible obviously, but yes, maybe there is some traffic conditions obviously there. Due to this actually we are getting this low efficiency, but most of the time you can see it is more than 90%. So that is the nearly 90%, that is if we are using PMSM. So on that case we will get more efficiency on the motor side. There is a total MOSFET losses they have given. So all the validation data points actually they have given here. So this is very good paper. Actually they have given all the data points. See guys, the MOSFET losses are 65 watt. Sorry, the diode losses is 65 watt. Then the MOSFET losses is nearly 1 kilowatt. Rate of change of SOC, how SOC is actually changing from 95% to up to that is nearly around 55 or 50% during the distance 0 to 32 kilometer. So SOC estimation algorithm, right? So all the things actually they have given. So this is how actually this overall means 8 to 9 parameters, and within these parameters there are multiple considerations. So whenever suppose we are planning to design a EV, we have to take this overall things, right? Depending on the road, depending on the every conditions, actually we have to calculate this all of these things. So guys, is there any question regarding this? Please, you can ask. So today we covered all the left things, that is DC-DC converters, traction inverter. See, it is basically a different industries are there who are specially suppose focused on the means algorithm parts, right? To basically detect or to basically give the range estimations. So on the EMS control algorithms, EMS controlling sections, actually that is different. Traction inverter control, that is different. BMS, that is different. Charger onboard or offboard, that is different. Vehicle body structure or chassis design, that is different companies. So battery pack designing, overall battery pack designing, that is different. Cell manufacturing, that is different. So there are multiple uh, domains actually are there. So for electrical electronics, for mechanical, for CS, so you have to select your choice, obviously, means in which domain actually you want to enter. And depending on that, you should have started with the in-depth analysis. So that obviously whenever, suppose after in the final year or during your whatever the placement drives will be there, or maybe suppose you are applying via LinkedIn or any kind of other options. So on that case, you can obviously, and suppose you have done a practical project on this. Suppose you have designed a charger, or suppose your overall team design a EV as well. Suppose two-wheeler you have designed, battery pack you have designed, so or inverter you have designed. So obviously it will impact a lot. So is there any question, guys, up to now? Please, you can ask. Okay, so there is no question from your side, guys. Okay, then I can stop sharing my screen. Okay, guys, thank you so much. Thank you so much for joining these overall sessions. So I hope you can get a lot of topics, right? A lot of we can say the variations of means you have taken the sessions from the EV itself. So obviously in EV there is a multiple things actually you learn. I hope especially the battery technology and in these things. So I hope you guys enjoyed a lot in this. So from tomorrow onwards, there will be a AV section that will be taken, obviously. That is the autonomous vehicle. So thank you guys. Okay, Sushmita, I am just turning off and I am concluding the session.
Yeah, thank you. Yeah, thank you,
Yeah,
sir.
thank you.
Thank you so much for all this 8 days of wonderful session. I hope the students has learned so many things from your EV session. Thank you so much, sir. On next SDP or FD, please, sir. The are there. So much, sir. Students has informed the last day for the electronic vehicle, electrical vehicle. From tomorrow, we are the new year is going to take a session. Is on AV, autonomous vehicle. Okay. So I request please join the session as usual with the same link by tomorrow as we do have a session still 7 more days. We are starting from AV tomorrow. Okay. We'll wind up the day. Thank you. Thank you for joining. Good night. Thank you so much, sir, once again.